Pro Electrician, number 6. This is chapter 6 on conductors. Here shown are the technical terms for the chapter and the objectives. In this chapter, you will explore the part of the electrical system that provides the pathway and connecting means between the electrical source and the utilization equipment. Conductors. Conductor refers to copper, aluminum, or copper-clad aluminum wire that carries current. If this wire is encased in a non-current carrying material, it is referred to as an insulated conductor or cable. A cable is actually a complete wire assembly having a conductor insulation, shielding if needed, and an outer protective covering. Cables can contain one conductor or many separately insulated conductors. For these, see figure 6-1 on the screen now. NEC Note 100, conductor is an insulated or a conductor is encased within a material of composition and thickness that is recognized by this code as electrical insulation. There are 3 classifications of conductors discussed in this text. Their uses are illustrated in figure 6-2. The service entrance conductors. These conductors deliver electrical energy from the utility company distribution supply conductors to the service entrance equipment. These are the conductors between the point of supply and the main service disconnect. Feeder conductors. These conductors, called feeders, conduct electrical current from the main service disconnect to the final circuit over current device, usually at the branch circuit distribution panel. Feeders are further categorized as main feeders, those originating at the service disconnect, and sub-feeders, those originating at the distribution panels other than the service equipment and connecting to other panels in the system. Conductor and cable classifications. Conductors are identified by letter codes such as THW, THHN, and XHHW, for example. These letter designations identify the type of insulation and the appropriate environments for which the conductor can be used. Some of the letter designations indicate insulation composition, such as A for asbestos, MI for mineral insulated, R for rubber, T for thermoplastic, V for varnished cambric, and X for cross-linked synthetic polymers. Letters also identify the physical characteristics of the conductor, such as H for heat resistance at 167 degrees Fahrenheit, HH for heat resistant at 194 degrees Fahrenheit, UF appropriate for direct burial, W appropriate for wet conditions, and C for corrosion resistance. Letter designations also indicate the type of outer jacket, sheath, outer covering, and overall outer layer, such as AC armored cable having an interlocked metal sheath, L for lead covered, MC for metal clad, N for nylon jacket, and NM for non-metallic sheath. Numerous other letter designations are included in table 310.104A, that is of the 2011 NEC. Conductor applications and installations rated at 600 volts of the code. Letter designations are marked on the product for easy identification. For example, THHN is a conductor having a thermoplastic high heat resistance of 194 degrees Fahrenheit, the insulation and nylon or equivalent jacketing. THW indicates a thermoplastic heat resistance insulation that can be used in wet locations. UF is suitable for underground or directly buried feeders. USE is underground service entrance cable. Conductor size designation. The size of a conductor is determined by its cross-sectional area. There are 2 methods of expressing conductor size, the American wire gauge and circular mills. Within the American wire gauge or AWG system, the smaller the number, the larger the wire. For proper wiring, 14 AWG is the smallest size used in commercial wiring. Control wiring may be smaller sizes, such as 16 or 18 AWG. The AWG system designates wires as large as 4-oct AWG. Larger wires are designated by their actual cross-sectional area in terms of kc mils or thousands of circular mils. A mil is 0.001 inch or a thousandth of an inch, and 1 inch is 1000 mils. The circular mil or 1c mil is equivalent to an area of a circle 1 mil in diameter. This is a very small area. As you can see on the screen, table 8 of chapter 9 of the code is shown, figure 6-3. The first column of the table contains wire size from 18 AWG through 4-oct AWG. The sizes are expressed as AWG. The corresponding area in circular mils is shown in the second column. This area is the actual area of the conducting material. For stranded conductors, the voids between the strands are not included. The sixth column contains the overall area expressed in square inches. This area includes the voids in stranded conductors, so it is slightly larger than the circular mils area. See figure 6-4. Shown on the screen now. Conductors larger than 4-oct AWG are expressed in 1000 circular mils or kc mils. Conductors that are 250 kc mils or 250,000 c mils are larger than 4-oct AWG conductors. 211 600 mils or c mils 211,600 c mils is the same again as the 4-oct AWG conductor. The relation between the inches and mils can be easily calculated. You can see that on the screen where 1 mil equals to 1 mil equals 0.001 inch. 1 inch equals 1000 mils. 1 c mils equals 0.785 mil squared. 1 mil squared equals 0.000001 inches squared. Finally, 1 inch squared equals 0.000000785 c mils. Just to discuss a sample problem 6-1, determine the area of a 6 AWG copper conductor in square inches. The solution is to, from table 8, the area of a 6 AWG conductor is 26,240 c mils. Again, you can find that in table 8 of chapter 9 of the NEC. To convert this to square inches, multiply c mils by 0.000000785. Again, that is the equivalent of 1 square inch. So in this case, 26,240 c mils times 0.000000785 equals to 0.0206 square inches. This value differs from the 0.027 inches squared shown in table 8 because the calculated value is the equal area of the strands. The area in the table includes the voids between strands. Quick note from the NEC, note 100, copper-clad aluminum conductors. Conductors drawn from a copper-clad aluminum rod with the copper metallurgically bonded to an aluminum core. The copper forms a minimum of 10% of the cross-sectional area of a solid conductor or each strand of a stranded conductor. Again, the chapter on that dedicates itself to definitions of each electrical term is in article 100 of the NEC or chapter 1. Conductor materials. There are three types of conducting materials used for general wiring, that is copper, aluminum, and copper-clad aluminum. Copper has excellent electrical and physical properties. It has been used as a conductor from the earliest efforts to conduct electricity. Aluminum is a good conductor, but must be installed with additional care and preparation. Aluminum must be cleaned just prior to terminating due to the rapid oxidation of the freshly exposed surface. Exposed aluminum at terminals should be coated with an antioxidant. In addition, aluminum connections tend to deform and loosen more than copper connections. If installed properly, aluminum conductors are dependable and economical. Aluminum has a greater resistance than copper, requiring a larger size to equal the same ampacity as copper, generally 2 sizes larger. For example, a 2-aught AWG copper conductor will carry 200 amperes, whereas a 4-aught AWG aluminum conductor could be required to handle the same current. A warning: improperly connected aluminum conductors can deteriorate with time and cause problems in the electrical system. Always use devices approved for use with aluminum conductors and follow proper installation procedures. Flexible cords and cables. Flexible cords fall into one of three categories: for extra hard usage, for hard usage, and for not for hard usage. Table 400.4 of the code lists some properties of the various types of cords. The ampacities of the different cords are found in table 400.5a1. When using these notes or tables, when using these tables, note that the equipment grounding conductor or the neutral, when using these tables, note that the equipment grounding conductor, neutral, and bonding conductors are not counted when determining ampacity ratings of cords. Cords and cables are permitted to be used as pendant wiring, fixed gear wiring, appliance connections, portable lamp or utility light connections, data processing equipment connections, elevator wiring and cabling, crane cabling, and hoist wiring. Cords and cables may not be used as a substitute for permanent wiring. Generally, they may not be concealed, be permanently attached, or pass through walls, floors, or ceilings. They should be continuous and unspliced and should not be used as taps. Cords generally do not require a separate overcurrent protection device. The branch circuit fuse may serve as the sole protection for the cord. The grounded neutral conductor in a cord must be identified with a white or neutral gray separator. The equipment grounding conductor, which serves to ground the non-current carrying parts of the cord supplied equipment, must always have a green color in the insulation covering or braiding. Except for double insulated equipment, an equipment grounding conductor must be provided in flexible cords. As you can see on the screen, figure 6-5 lists some devices that may be cord and plug connected. Code requirements for conductors. In the code, Article 310, Conductors for General Wiring, addresses the general requirements for conductors. Conductor designators or conductor designations, temperature considerations, environmental conditions, size limitations, ampacity, installation methods, material usage, insulation, and other factors concerning conductors. Refer to Article 310 when planning any residential, commercial, or industrial wiring installation. Bare conductors. Bare conductor or a bare conductor is a conductor with no covering or electrical insulation. Per section 230.41 of the code, conductors for general wiring must be insulated except in the following situations. The grounded neutral conductor may be bare when used as a service entrance conductor to ground or on non-current carrying service entrance components such as the service head, raceway, meter enclosure, or main service disconnect enclosure. For that, see figure 6-6 shown on the right side of the screen. Secondly, a bare conductor is permitted as the grounding electrode conductor for service entrance equipment. Again, see figure 6-6. Third, a bare conductor is allowed for purposes of grounding the non-current carrying parts of equipment such as dryers, ovens, and stoves. For that, see section 250.118 of the code. Fourth, a bare conductor may be used to bond the non-carrying carrying components, boxes, enclosures, equipment frames, and motor skids of the electrical system. Finally, a bare conductor is permitted as the grounding means for load side equipment and sub-fed panel at a sub-fed panel. NEC notes of the 100 Article 100 conductor is a bare conductor is a conductor having no covering or electrical insulation whatsoever. Stranded and solid conductors. Conductors 8 AWG and larger that will be pulled through raceway or raceways must be stranded. The conductors need the flexibility when being pulled around offsets and bends. Solid conductors are too rigid in larger sizes to afford much flexibility. NEC Note 310.3, where installed in raceways, conductors of size 8 AWG or larger shall be stranded, exception as permitted or required elsewhere in this code. Parallel conductors. It is often more feasible and economical to run conductors in parallel because of larger feeder load requirements. Conductors run in parallel must meet the following criteria. The conductors must be 1/0 AWG or larger. The conductors must be the same size. Conductors must have the same insulation type. Conductors must be the same material. The conductors must be the same length, and the conductors must be terminated in the same manner. Parallel conductors can be installed in separate conduits or in a single conduit. If the conductors are installed in the same conduit, the electrician should observe section 310.15b3a of the code regarding allowable ampacities of conductors. The conductor size limits, with some exceptions, section 310.106a of the code lists the smaller conductors permitted for general wiring as 14 AWG copper or 12 AWG aluminum or copper-clad aluminum. The exceptions allow smaller sizes for flexible cords, fixture, wire, fractional horsepower motors, cranes and hoists, elevator control and signal circuits, remote control circuits, protective signaling, and motor control circuits. The table in figure 6-7 contains a minimum conductor sizes. Shielding. The code states that conductors operated above 2000 volts in permanent installations must have a ozone resistant insulation and be shielded. Further, those with metal shields must be grounded. Direct burial. Section 310.10f of the code states that conductors used in direct burial applications must be specifically approved for the purpose. In addition, these conductors, if rated above 2000 volts, must be shielded and the shield properly grounded. However, direct burial conductors rated between 2000 volts and 5000 volts do not require shielding if the cable has an overall metallic shield or armor. Wet locations. Conductors used in wet locations must be either lead covered or marked with a W RW, TW, and THW, for example, indicating they are suitable for wet locations. NEC notes: wet location, installations underground or in concrete slabs or masonry in direct contact with the earth, and locations subject to saturation with water or other liquids, such as vehicle washing areas and unprotected locations exposed to weather. Corrosive conditions. Conductors that will be used in severe environments in the presence of corrosive agents and in situations where insulation deterioration is likely must be covered with insulation specifically listed and suitable for such conditions. These conductors are marked with a C. Temperature limitation. Section 310.15a3 of the code prohibits the use of any conductor in any manner where its operating temperature will be greater than that designed for its insulation type. Further, different conductors are not to be associated together in a way that would cause the limiting temperature of any conductor to be exceeded. The operating temperature of a conductor is determined by the heat produced by the resistance to current flow and the rate at which this heat is dissipated to the surroundings. Greater current flow and greater resistance in the conductor produce more heat. An aluminum conductor will produce more heat than a copper conductor of the same size with the same currents because the aluminum conductor has greater resistance. Several factors affect the rate of heat dissipation. The warmer the temperature of the surrounding air, or of the temperature of the air surrounding the conductor, the less heat is dissipated. Again, several factors affect the rate of heat dissipation. The warmer the temperature of the air surrounding the conductor, the less heat dissipated. If there are many conductors close together, they will all release heat, raising the temperature of the surrounding air, reducing the amount of heat they can release. Insulation greatly reduces the heat flow between the conductor and the surrounding air. Conductor marking. All conductors and cables must be marked to show the following information. First, maximum rated voltage. Second, the proper letter designation for the type of wire or cable. Third, the manufacturer's name, trademark, or other distinctive marking by which the organization responsible for the product can be readily identified. Fourth, the size of conductor in AWG or circular mill area. Cables are marked with surface markings, tape, or tags. The type of marking is determined by the type of cable or conductor. Refer to section 310.120b of the code for the type of marking required for a specific cable or conductor. Conductor identification or color. Grounded conductors, neutral, 6 AWG or smaller, must be insulated white, gray, or 3 continuous white stripes on other than green insulation along its entire length. Larger sizes may be white, gray, or 3 continuous white stripes, or may be painted white at all junction termination locations. Equipment grounding conductors that are insulated must be insulated solid green or green with yellow stripes if 6 AWG or smaller. Larger sizes must be either bare at all boxes and outlets or have the insulation painted green at every box and outlet. See section 250.119 of the code. Ungrounded or hot conductors may have insulation of any color other than green, white, gray, or green with yellow stripes. Notes per 1110.15 of the code, the high leg of a 4-wire delta distribution system must be identified with orange markings. Conductor application. Application and installation types for conductors are listed in Table 310.104a of the code. Consult this extensive table prior to installing any wiring. The table gives several attributes for insulated conductors: trade name of the insulation, letter designation assigned to that type of insulation, the maximum operating temperature allowable for the type of insulation or outer covering, the conditions suitable for application, the insulation composition, and the size availability. Also, the insulation's thickness and the outer covering are also conductor application details. Again, for that, see Table 310.104a. Allowable ampacities in conductors. Very important part of the NEC. It is a series of tables and articles that you will very often visit and review and use. The tables found in section 310.15 are used to compute size and ampacity of conductors rated under 2000 volts. As we proceed, refer to the tables, which are included in the reference section of this text. Each table is used for a different type of conductor. First one is Table 310.15b-16. Again, Table 310.15b-16, used for up to 3 insulated conductors installed in raceway as multi-conductor cable within raceway, in air, or directly buried. This table is based on a surrounding temperature of 86 degrees Fahrenheit or 30 degrees Celsius. Again, pay very close attention to the title of each table. Each table is slightly different in the amount of conductors that they're referring to within a raceway, for example, a conduit or cable tray. For example, some may be no more than 3 current carrying conductors, which are your hot cables or conductors. Other tables may be only a single conductor, and others are more than 3 conductors for different temperatures. You got to look at the temperature for that table as well. The ambient temperature sometimes could be 30 degrees centigrade or 86 degrees Fahrenheit. Sometimes it could be a lot more than that. So make sure you make that distinction between the tables and follow the correct table to find your allowable amperage. Table 310.15b-17. Ampacities for single insulated conductors installed in free air. The ambient temperature is also 86 degrees Fahrenheit or 30 degrees centigrade. The outside overhead wiring is sized using this table. Table 310.15b-18. Again, 310.15b-18. This table contains ampacities for 3 single insulated conductors in a raceway or in a cable whose insulation range temperatures are 302 degrees Fahrenheit to 482 degrees Fahrenheit. That is 150 degrees C to 250 degrees C, and based on an ambient temperature of 104 degrees Fahrenheit or 40 degrees C. The conductors used for general wiring that have an insulation range of 140 degrees Fahrenheit to 194 degrees Fahrenheit, that is 60 degrees C to 90 degrees C. And finally, table 310.15b19, ampacities for single insulated conductors in free air having conductor insulation temperature ranging from 302 degrees Fahrenheit to 482 degrees Fahrenheit, that is 150 degrees C to 250 degrees C. This table is based on an ambient temperature of 104 degrees Fahrenheit or 40 degrees C. Section 310.15 further explains and modifies the values found on these tables. To find the ampacity of a conductor, simply read down the vertical column indicating the type of conductor, its temperature rating, and the insulation type to the horizontal row indicating its size. Normally, conductors are selected for a known load. The ampacity of the selected conductor must be greater than or equal to the specified load. Sample problem 6-2. Determine the rated ampacity for each of the 2 AWG type THW copper conductors installed in Conduit. The solution is in table 310.15b16, where a value of 25 amps is found in the 12 AWG row of the copper THW column. The allowable ampacity of each of the 12 AWG copper conductors is 25 amps, as you can see using this table. The next problem, 6-3, sample problem. 3 aluminum type THWN conductors have been specified to carry 65 amps through rigid non-metallic conduit. What size would the conductors be, or what size are the conductors needed? The solution is looking in the aluminum THWN column of the table 310.15b16. 65 amps is found in the 4 AWG row. As you can see, those have been indicated, highlighted in the problem, in the table. Therefore, the 4 AWG aluminum THWN conductors are the smallest conductors allowed. Ampacity correction factors. The allowable ampacities listed in tables 310.15b16 through 310.15b19 are only applicable for a specific number of conductors. One conductor in tables 310.15b17 and 310.15b19. 3 conductors or less in the other 2 tables. And a specific ambient temperature of 86 degrees Fahrenheit, that is 30 degrees C, in tables 310.15b16 and 310.15b17, and 104 degrees Fahrenheit, that's 40 C, for the other 2 tables. When there are more than 3 conductors in the raceway, or the ambient temperature differs from the table values, corrections must be made. Table 310.15b2a contains temperature correction factors. Figure 6-8 shown now on the screen. Ambient temperatures are listed on both sides of the factors. Celsius on the left and Fahrenheit on the right. The correction factor is multiplied by the allowable ampacity from the table to determine the allowable ampacity for a different ambient temperature. The ampacities of different conductor types vary differently with temperature change. Therefore, each type of conductor has unique temperature corrections. As the ambient temperature increases, the ampacity of the conductor is reduced. Conductors installed close together as in a raceway, are exposed to heat generated by the surrounding cables. This heat is not readily dissipated because the air in the conduit is fairly still. Section 310.15b3a includes adjustment factors for more than 3 conductors in a raceway. Figure 6-9. Again, multiplying this correction factor by the allowable ampacity for 3 or less conductors obtains the actual allowable ampacity. In the code, this correction factor is expressed as a percentage rather than a decimal value. And as you can see, here are some sample problems. 6-4. The problem is to find the maximum allowable ampacity for 6 1AWG THW copper conductors in a single conduit installed along a ceiling with a boiler room, or the ceiling of a boiler room with an ambient temperature averaging 125 degrees Fahrenheit, that's 52 degrees C. For the solution, first find the unmodified allowable ampacity from table 310.15b16, as you can see on the left side of the screen. The units are highlighted. The allowable ampacity in this case is 130 amps. And as you can see on the bottom right, the problem is continued. For 1 AWG-THW copper conductor, the allowable ampacity is 130 amps. Then determine the correction factors. Temperature correction factor is 125 degrees Fahrenheit, which equals 0.67. The number of conductors correction factor, in this case is 6, equals 2.80. So by multiplying the unmodified allowable ampacity by the 2 correction factors, the modified allowable ampacity is obtained. In this case, we get 70 amps, or 130 amps times 0.67 times 0.80, which is 70 amps. Ampacity adjustment factors. There's a table 6-9 shown on the screen, showing the allowable ampacity is reduced when a raceway or cable contains more than 3 current carrying conductors. When working with the correction factor for multiple conductors in a conduit, not all conductors are included in the count. Equipment grounding conductors and the neutral conductor in single-phase 3-wire circuits are not counted because they normally carry no current. Therefore, they generate no heat. Neutral conductors that regularly carry current are counted, however. Voltage drop. Most electrical equipment is sensitive to variations in line voltage. In order for the equipment to operate effectively, it is important to supply the correct voltage. The code suggests but does not mandate a maximum voltage drop of 3% for any feeder or branch circuit, and a maximum combined voltage drop from service entrance to final utilization outlet of 5%. Many factors affect voltage drop: temperature, conductor length, conductor size, and conductor material. However, the greatest cause of voltage drop is conductor resistance, which is proportional to the current. The primary remedy for voltage drop is to reduce the resistance of the conductor by increasing its size or diameter. Voltage drop can be reduced in other ways, such as reducing ambient temperature, shortening the length of the conductor, and changing the conductor material, but these methods are less practical. Calculating voltage drop. Voltage drop is calculated using Ohm's law. Again, E, or voltage, equals to current times resistance. The conductor resistance is listed in table 8 of chapter 9 of the code. which was shown in figure 6-3. You can rewind to review that or look it up again on chapter 9, table 8. Note, table 8 lists DC resistance rather than impedance, which includes resistance and reactance. The voltage drop formulas assume no reactance and a power factor of 1. There are two categories of copper in the table, coated and uncoated. Tin coated copper is often used for conductors having rubber insulation to prevent chemical reaction between the copper and the rubber. Most copper conductors are uncoated, however. Single phase voltage drop. Single phase voltage drop can be calculated using the formula shown on the screen, where VD equals voltage drop, L equals one-way length of conductor in feet, I current in the circuit in amps, and R is the conductor resistance as shown in table 8, chapter 9 of the code, shown in ohms per 1000 feet. In a single phase system, current travels along the conductor and then returns on the neutral conductor. Therefore, the current travels from the source to the equipment and then back again. The total distance traveled is twice the length of a single conductor. So a factor of 2 is added to the equation. The entire product must be divided by 1000 because the resistance is based on a length of 1000. That's 1000 feet. By dividing the actual length in feet by 1000 and multiplying by the resistance per 1000, the actual resistance of the conductor is determined. The voltage drop equation can be algebraically rearranged and to create an equation to determine the maximum allowable resistance to have less than 3% voltage drop for a given conductor run. And that equation can be seen at the bottom of the screen, where resistance maximum equals to 1000 times 0.03 times the line voltage, all divided by 2 times the length times the current. Again, the length is the one-way distance in feet. Going over sample problem 6-5, determine the voltage drop on a 20 amp circuit having a length one-way of 170 feet. 10 AWG THW stranded copper conductors and a single phase 120 volt power supply are used. The solution for this problem: from table 8, chapter 9, the resistance for 10 AWG stranded copper conductor uncoated is 1.24 ohms per K feet, or 1000 feet. Those have been highlighted on the table itself. So using the equation presented in the previous discussion, VD equals 2 times length times current times resistance divided by 1000. Plug in the values, in this case 2 times 170 times 20 times 1.24 divided by 1000 gives you 8.4 volts. To determine the voltage drop as a percentage of the total voltage, divide the voltage drop by the total voltage. So in this case 8.4 volts divided by 120 volts is 0.07, which is 7%. The code recommends a maximum 3% voltage drop. It would be advisable to rewire this circuit using a number 6 AWG copper conductor, which would reduce the voltage drop to an acceptable level. So using the voltage drop formula again, using a larger conductor, in this case 6 AWG, which gives you a different resistance, or a different ohms per 1000 foot resistance of 0.491, plug in the rest of the values to the formula, we get 3.3 volts of a voltage drop. And to find out the percentage, we divide that by 120 volts, gives us 0.0275, which is 2.75%, which is less than 3%, and this is acceptable. For three-phase voltage drop calculations, in a three-phase system, voltage drop is calculated with a slightly different equation. In this case, VD equals to the square root of 3 times L, which is the length of in feet one way, times current times resistance, divided by 1000, all divided by 1000. There's another formula, VD equals 2 times 0.866 times length times current times resistance, all divided by 1000. Again, VD is the voltage drop, L is one-way length of conductor in feet, and I is the current in circuits in amps. And R is the conductor resistance as shown in table 8, chapter 9 of the code in ohms per 1000 feet. In the three-phase wiring, two current carrying conductors are connected to the equipment. These two conductors are supplying current that is not in phase, so the resulting current is the square root of 3 times the nominal current. The current is grounded at the equipment, so the factor of 2 of the length is unnecessary. The second form of the equation shown is identical to the first because 2 times 0.866 is the same as the square root of 3. To determine the maximum allowable conductor resistance and to maintain a 3% voltage drop in a three-phase system, use this equation shown on the bottom right of the screen, where R max, resistance maximum, equals to 1000 times 0.03 times the line voltage, all divided by the square root of 3 times the length one way times the current. These are very, very useful and important equations. I would recommend you save them or memorize them. Have them readily available. Sample problem -6. A 2 ampere panel must be fed from a source or switch gear that is 460 feet away. The switch gear supplies 208/120 volts, 3-phase 4-wire power. What size THW conductor copper is needed for the feeder? Assume 3% maximum voltage drop. So for the solution, first determine the maximum allowable resistance for the conductor in this three-phase system. For that, we use the formula R max equals to 1000 times 0.03 times the line voltage all divided by square root of 3 times the length times current. Plug in all of the known values. In this case, all of them are known. We get 6240 divided by 159,349, or 0.0392 ohms per 1000 foot. So checking table 8, chapter 9 for a resistance less than 0.0392 ohms per k feet. For an uncoated copper conductor, we see that 350 kc mil conductor, or 0.0367 ohms per k feet, is the smallest allowable size. You can see that highlighted on the table shown. Again, table 8, chapter 9 is a very important table. Make sure you have very convenient access to it. Conduit capacity. Of the many methods of wiring used in commercial installations, conduit is used most frequently, either as the sole method or in conjunction with other systems. The required conduit size depends on the conductors to be routed. There are three factors involved when sizing conduit. The first is the allowable conduit fill or percentage. Second is the total cross-sectional area of the conductors. And the third is the number of conductors within the conduit. These three factors determine the conduit size. Several tables from Chapter 9 of the code are needed to size conduit. Table 1, maximum allowable fill in conduit. Table 4, the total and allowable areas for different conduit types and sizes. And finally, Table 5, conductor diameter and areas. Given the number and size of conductors, the conduit is sized using a two-step process. First, the total area of the conductor is calculated. Then the conduit size is selected. Area of conductors. Table 5 in Chapter 9 of the code contains the cross-sectional area for conductors. The table is organized by conductor type and conductor size. Determining the area of the conductor is easy. First, find the type of conductor in the left column, then find the size and read the area in the far right column. When you're determining the total area of all conductors in a conduit, repeat this process for each conductor to be contained in the conduit. Then add the areas of all of the conductors together to determine the total area, the total conductor area. To go through this sample problem 6-7, 112 AWG THHN and 110 AWG THHN and 3 8 AWG THHN conductors are to be run through rigid metal conduit RMC. Determine the total area for the conductors. For this, you use Table 5 to find the conductor areas. You can see those highlighted. You add those up. For example, in this particular example, we have 12 AWG THHN. We have one of them with an area of 0.0133. For the 10 AWG THHN, we have another one, just one, with an area of 0.0211 square inches. And for the AWG THHN, we have three of them, so multiply 3 times its area of 0.366 inches squared, we get 0.1098 inches squared. So we add those, all of those areas, we ultimately get 0.1442 inches squared. So that is our total area. Minimum conduit size. Table 1, Chapter 9 of the code shows the allowable percentage of conduit area that can be filled with conductors. The area that can be filled is based on the number of conductors. The different percentages are the result of the geometry involved in circular conductors with a circular conduit. For that, see figure 6-10. Once the allowable percentage of fill is known, Table 4 in Chapter 9 of the code is used to find the minimum allowable size for the type of raceway being used. Raceways larger than the minimum required size can be used, but this normally will be uneconomical. To go through the sample problem, 6-8, the last one for the chapter, 112 AWG THHN, 110 AWG THHN, and 3 8 AWG THHN conductors are to be run through a rigid metal conduit RMC. Determine the smallest conduit size that can be used. For this, the total conductor area is 0.1442 square inches. See sample problem 6-7. The table 1 shows that the conductor area must be 40% or less for the conduit cross section. That is because we have over 2 conductors. So under rigid metal conduit or RMC in table 4, when filled with more than 2 conductors, 3/4 inch conduit can carry conductors with a total area of 0.220 square inches. This is the smallest size that can carry at least 0.1442 square inches. So the 3/4 inch conduit is the best size in this case. These are the review questions for the chapter. Do go over them. Make sure you're familiar with each of the answers, how to find them. Make sure you're comfortable in finding information and answers not only in the text of the book, but also using the NEC, whatever version you may be using. We recommend using 2011 or later for the purpose of training and education. If you are going to be using the NEC on the job, make sure that you use the latest version or the one that is directly applicable to the project that you're working on. It may be either the latest. In some cases, some rare cases, you are required to use prior year national electrical codes. Make sure you pause the video if you need more time or if you need to review the answers for these 3 questions in detail. This section is the using the NEC section. Is basically these are problems for you to become familiar looking for information in the NEC and solving problems using information from the NEC. So make sure you do go through each of these, and if you would like, find the information on your own in the NEC and solve the problems on your own. The answers are here provided for you to check, to cross-check. Do pause the video if you need to review these in detail. And again, I do recommend for you to go back and not only do these problems, answer these problems, but to make sure that you are comfortable looking for information in the NEC. A recommendation I have is to use the electrical or PDF version of the NEC that has live or links in its table of contents that take you straight to chapters. Some of the newer versions using electronic versions for the NEC, you can look up words using the PDF. You can look up terms, and again you can click on the various chapters, even tables and subsections of chapters, and takes you straight to it without having to flip through pages. And this is the end of the lesson. Thank you very much for going through it, and I do encourage you to look for the next lesson and complete that and the rest of the lessons for the course. Thank you very much.